in this video, we want to talk about iterations and subframes or substeps. And what this is about is basically the precision of the calculation in the Vellum solver. And when we look at the Vellum solver, right in the very first tab, we can see a couple of things that kind of clearly stand out as some kind of precision parameters, and that is substeps, constraint iterations, smoothing iterations, collision passes, post-collision passes, and polish passes, and so on. So I will not talk about each of them because, for example, the smoothing iterations and the polish passes, as you can imagine, are basically just kind of a final smoothing out dents and all that after the simulation. So I will ignore them for now because they're not super important. But what I want to talk about is substeps, constraint iterations, and collision passes, because I think those three are the most important to understand. Now, spoiler alert, it's actually in practical terms not as complicated as you might think, because in the end the safest bet is always to increase the substeps, and because Vellum is really fast, it's actually fine most of the time to just work with them. Nonetheless, I want to talk about the difference between the substeps, the constraint iterations, and the collision passes. Now, the first thing we have to understand, and I think we talked about this a little bit when we talked about what constraints are, they are basically three elements in a Vellum simulation specifically, and later in the RBD simulation as well, that are fighting each other more or less. And that is forces, collisions, and constraints. They kind of all want different things. So for example, the force we already have in this simulation here, where I have just a planar patch, nothing special here, a planar patch with that kind of resolution and some geometry that are moved and scaled to this position. And when I run this with the default settings, surprise, the cloth falls on our statue here and covers it. Nothing special. And also, as you can see, no problem at all. Now, what happens here is three things. Actually, the force that drives the whole thing is the gravity. It pulls the cloth down. Then what stops it from moving in the direction of the force of the gravity is the collision. So the object itself, of course, stops every point from moving further down. And then there's another thing that stops the point to move further. For example, this point here has no collision, but it still doesn't move further. It stays more or less where it is. Well, not quite, but you know what I mean. It doesn't move further down. It moves to the side, back and forth. And of course, the reason for that is that there is a constraint that connects it with its neighbors. So we can, of course, visualize those constraints. We've seen that before. In the beginning there they are. We can even see what comes out of it. So these are the constraints. And as you can see, each of them kind of wants something else. There are, for example, cases where a collision stops a constraint from reaching its desired situation or desired state, as we've seen before. So that's the best way of thinking about it. The three things, forces, collisions, and constraints, fight each other. And this is exactly what this is about. Basically, it says how often the three things are allowed to be calculated. And this kind of influences who wins the fight. To show this a little bit, let's look at the collision passes. And one thing you have to understand, that there are two collisions happening actually, before the whole constraint stuff and forces are calculated and afterwards. And this is why there are two. So it's in the beginning of the frame, roughly speaking, and the end of the frame. And to prove that, I can turn off the collision passes to 0. And you would expect, if there are no collision passes calculated, that it falls through, but it doesn't. You can see it's a bit weird and it looks strange, but it doesn't happen. And that is because there are still post-collision passes that are now kind of calculating the collision. If I set this to 0 and run it again, you can see during the simulation there is no calculation that takes care of collisions. And if I set this to too low, then the collision will simply be not very accurate. For example, you can see that here there is a collision happening, or not happening actually, where it should happen. Now, of course, the numbers that side effects chose here are pretty good and pretty fast and give, on average, the best results. And to be honest, it's not worth talking about collision more than that. In the unlikely case, and personally I never had that you see collisions not happening, so intersections, you could increase those two numbers I think the first collision passes is a bit faster than the second one, and this one, as far as I can tell, is the most important, as we've seen. For example, let me quickly show you that. If I turn off the post collisions and only leave the pre-collision passes, let's call them, you can see that it's not actually fully working. This is more like a helper collision process. The most important ones are at the end of the simulation. So I will not talk further about this than that. Just keep that in mind about collision passes. More interesting are actually the constrained iterations versus the substeps. So the substeps, really quickly, is actually basically you increase the number of calculations of all three. The forces are calculated more often, not more precisely actually, as far as I can tell, but more often. And that's important. The constraints are calculated more often and the collisions are calculated more often when you increase those substeps. That in turn means that the result will be different because basically the precision overall is changing. So let's actually quickly try that and increase that to 10. And see if we get the same result. And we've seen that before. It's not. I mean, of course, it's slower, but also the calculation is actually technically more accurate because those are actually the results we would get from the default cloth settings we have here, which are the defaults. I didn't change them from the Vellum cloth constraint. And the reason why this result is now different is basically that the whole calculation is happening more often. And in theory, what you would do is you would increase that number to a point where the results don't change anymore, because then you know you have the most precision. Now, in my experience, in practical terms, it's not actually important to be precise in a normal day environment. It's more like, how do I get what I want? So this is something beginners often misunderstand. We're not doing physics simulation like scientists do. This whole thing here is scientifically pretty inaccurate. It's really just a rough estimation, which means there's nothing wrong with keeping the substeps at 1 if this behavior is exactly what you want and if you decide that this looks good in your simulation. Fair. That's good. If it works, it's not wrong. Move on. This is now your simulation and you like it. Just keep in mind, when you increase the substeps for some reason, that your results will change because of the reasons we just explained. Now, let's give this whole simulation a bit more to work with. Let's challenge it a bit more. And to do that, I switched to forces and want to change the gravity to something really insane, like -1,000. So we're on some kind of, planet where the gravity is insanely high. And of course, what happens, unsurprisingly, the stretching happens much stronger. And of course, the reason for this is that, and actually just go through with the arrow keys. The reason for that, of course, is that the force that pulls the points down is now stronger, which means luckily our collision still works. It's still accurate enough. But what kind of, well, I wouldn't say fail, but what loses in this fight are the constraints. So the constraints, of course, in our Vellum cloth here, try to keep and that is, of course, the stretch stiffness. It tries to keep the points together how they were in the beginning by a certain number, which is actually pretty high. It's 1 with 10 zeros. But it's not winning, and the reason is that it's not calculated often enough. Why am I saying it like that? Because you can actually increase the constraint iterations to a higher number, let's say 1,000. And that means that now during the whole simulation, the calculations of the constraints, not the forces or the collision, just the constraints, will happen 10 times more often. And as you might predict, that means that even with a 10 times stronger gravity, all of a sudden our results are still more or less correct compared to before, because the constraints are now not stronger. That's not the right way of thinking about it, but they're calculated more often, and therefore in the end, in the whole calculation, have a higher importance, let's call it. So as you can see, this actually solves our problem here, just increasing the constraint iterations. But the thing is, and I can't fully explain to you why that is, and to be honest, it doesn't really matter, why this totally works. And you can increase that to a number until you're happy and you feel like the results are like you would expect them. If we copy this whole thing and we don't increase the constraint iterations by 10, so we keep them at 100, but we just multiply the substeps by 10, you will see that the result is actually more accurate. And this is really just something in practical terms that you have to remember. More substeps are always in the end more accurate than more constraint iterations, even though they're technically almost the same. But simply the increasing the substeps means that the whole calculation internally, all the calculations are happening more often, and you get closer to a correct result. So as you can see here, this is the version with 1,000 constraint iterations, which, okay, it looks okay, you know, it's not wrong or anything. Everything we do is kind of wrong, but it looks kind of not nice, not believable, and that's actually really what we care about. And this is way more what we would expect. Now let's compare the performance of the two and make sure that you rewind and delete all the caches we calculated so far. Let's open the performance monitor and ignore what I have done before. Press record and let's go, I don't know, to frame 72. And let's see what comes out of this once it's calculated. So here are the results, and they're actually a bit surprising. You would think that the first version, where we only increased the constraint iterations, should be faster than the version where everything is calculated 10 more times. But it turns out it's actually faster to do it this way. The first version is about 13 seconds slower than the version where we just increased the substeps. And now finally, that begs the question, when do I need to increase the substeps? Basically, there are two cases in my experience. First and foremost, if you're not happy with the result. So for example, if you know that your constraints are set to the absolute maximum, and we've seen that before in your stretch stiffness, for example, and you get a result like this, where the stretchiness is just absurdly high for some reason, even though your constraint should have a very strong stiffness. In a case like that, where the numbers should be correct but the result is not, then of course increasing the substeps will get you closer to the result you expect. And another reason can be, which is kind of the same, in general, like always when we increase substeps, when you work with very high speeds. So, but that's the same thing really, because what you will see with very high speeds is the same kind of unnatural or overly strong stretching, and then you know that you have to increase the substeps. So again, my point is, if you feel like you're happy with the result, you don't necessarily need more substeps, but there are many cases where you will see that your results are not like you expect them, and then it's an obvious choice, and then you go with substeps. And you will get basically more precise result, as we can see here, but also, surprisingly, a faster result. So yeah, so that's to remember about all those iterations in substeps, and in short, just increase the substeps and you're fine. So I hope this was helpful. Thanks very much and see you later. Cheers.